all this stuff, everything shares something in common. Here's a favorite. It's a golden rectangle. You can't leave home without it.
Yeah, what's up, Zach? Oh, when you have one rabbit, you always have just one rabbit. But when you have two, look what can happen. So what do golden rectangles have in common with rabbits? About 800 years ago, a mathematician liked to invent problems, and he made one up about rabbits. His name was Leonardo, but he liked to be called Fibonacci. His father's name was Bonacci, so Leonardo was also known as Filius Bonacci, Italian for son of Bonacci. So you can see why he went by Fibonacci. Anyway, here's the problem that he made up. How many pairs of rabbits will there be at the beginning of each month if every month each pair produces one new pair that begins to bear young 2 months after birth? I'll show you. The first month, there's just one pair of rabbits. They're too young to reproduce, or they just don't know each other well enough yet. So the second month, there's still just one pair. Now we wait a month, give them a little privacy. And the third month, there are 2 pairs, the first pair plus a newborn pair. Now remember, the young ones must wait a month before reproducing. So the fourth month, add just one new pair for a total of 3 pairs. The next month, the first and second pairs both reproduce. So there are 5 pairs in all. Keep up this pattern and there'll be 8 the next month, 13 the next, and on and on and on and on. There's a pattern here. Do you see it? The next number is 21. All you do is add the first 2 numbers to get the third. Starting out, 1 plus 1 equals 2. Now add the next 2 numbers together. 1 plus 2 equals 3. 2 plus 3 equals 5, and so on down the line. You can keep this up forever. The numbers get really big very fast, but the pattern never changes. Now, rabbits really don't multiply that way. If they did, there'd be millions of rabbits in just a few years. And there just aren't enough carrots to go around. But Fibonacci did discover an interesting pattern. So they named the sequence of numbers after him, the Fibonacci sequence. The numbers in the sequence can be found all over, even in flowers. Count the petals on flowers and you'll often find Fibonacci numbers. This orchid has 1, 2, 3, 4, 5 petals around the center. This daisy has 21. Both are Fibonacci numbers. Look at this plant. Pick any stem, then count the stems around the branch until you get to the stem directly above where you started. 1, 2, 3 stems after spiraling around the branch 1 time. 3 and 1. Sound familiar? Try the same thing with the rubber tree plant, and you'll find 2 different Fibonacci numbers. 5 stems after going around the branch 2 times. Let's try this pineapple. See these scales shaped like hexagons? Each one is part of 3 different spirals. There are 8 gradually sloping spirals going around the pineapple this way, 13 steeper spirals going around this way, and 21 here. 8, 13, and 21. Fibonacci numbers again. If you look, you can find Fibonacci numbers in pine cones and artichokes too. But in music, these numbers are not only seen, they're heard. Look at a keyboard and you can find Fibonacci numbers. This is an octave that's made up of 8 white keys. 8, a Fibonacci number. In this octave, there's a group of 2 black keys and a group of 3 black keys. 5 in all. More Fibonacci numbers. And if you play the first, third, and fifth white keys, Fibonacci again, you can hear the harmony in the numbers. But get this. You can not only hear the harmony, you can see it. Let's use the Fibonacci sequence to make some rectangles. Take a Fibonacci number, let's say 5, and make it the height.
Use the next number in the sequence, 8, for the length. Let's make 2 more rectangles this way and see how they compare. Even though the rectangles are different sizes, they have a similar shape. We can compare the sides by writing the numbers this way. That's called a ratio. I can change the ratio to a decimal value that means the same thing. I divide the top number by the bottom number to find that decimal. I could do the division by hand, but some of these numbers go on and on. Let's use a calculator and save time. Let's see, 8 divided by 5 equals 1.6. 13 divided by 8 equals 1.625. And 21 divided by 13, that's about 1.615. I'm getting almost the same answer for each ratio, but I could have guessed that. They came from rectangles that look similar. I wonder if this works with larger Fibonacci numbers. Let's try 89 and 55. That ratio is also very close to the others. A rectangle with length of 89 and height of 55 would look similar, only much, much larger. These rectangles are getting closer to the shape of a special rectangle, a golden rectangle. And the ratio of the length to the height is approaching a special ratio, approximately 1.618, called the golden ratio. Rectangles with the golden ratio are golden rectangles. People have been using golden rectangles for ages. The ancient Greeks used them when they built temples like the Parthenon. Today we still find them in architecture and works of art. The result? Visual harmony. Where else can we find golden rectangles? Okay, thanks. There's one more golden rectangle that I want to show you. I carry it all the time. We all do. It's right here. Bend your finger like this, and it forms a golden rectangle. And in that golden rectangle, there's a golden ratio. You see? You can't leave home without it. Thanks. The human body is golden too. And no matter your size, large or small, you carry lots of golden ratios. Greg's a lot taller than I am, but we share the same golden ratio. Just compare the distance from our waist to the floor with the distance from our waist to the top of our head. Change the ratio to a decimal number, and it's close to a golden ratio for both of us. Try it with a friend. So we started out with a bunch of rabbits and discovered the Fibonacci sequence. Remember, it's a sequence that you get by adding 2 adjacent numbers to get the next number. Take any 2 numbers next to each other, divide them, and it's close to a golden ratio. Golden ratios make golden rectangles, which we're all familiar with by now. Look hard, because there are plenty out there. Trust me, my word and Fibonacci's are as good as gold.